Right, so thanks for your attention this morning. And what I'll tell you about is more forward-looking than typical talks. It's about the vision I see for a next step in deep learning that goes beyond the current capabilities, which you'll see I call System 1, and towards higher-level cognition, which would unlock better generalization and better understanding of the world around us by neural nets. So we've made amazing progress, mostly in perception and to some extent in natural language and also playing games. And some people think that we can just continue using the current techniques by growing the data sets, the sizes of the models, then computer speed, and so on. I don't think so. I think that we are still very far from human-level AI, not just in performance, but more fundamentally in some of the ideas that are missing in order to reach that level. And I think we can see some of the clues for this in what we call sample complexity. In other words, how many examples you need to learn a new task. We can see clues in the fact that we still depend on humans to provide the definition of high-level concepts by providing labels. And we can see that in some of the errors made by those systems, which humans would not make, sometimes very stupid mistakes, which illustrate that the understanding acquired by the machine is still not at the level of humans and maybe sometimes very superficial. An example of that, of course, is with adversarial examples. And then there are other people who think that the next step towards human-level AI is going to be very different from deep learning, that we need something else, maybe going back to human-level, to classical AI ideas. What I will try to tell you is that I think that we can approach some of the objectives of classical AI, of reasoning and high-level cognition, using the tools of deep learning, as well as probably some new ideas that need to be added. So basically what I'm talking about is extending deep learning towards higher-level cognition. Let's start by talking about compositionality, which was one of the keywords in my title. So what is that? In machine learning, we're trying to generalize to new configurations of variables. When you have only one variable, it's very easy. You don't have to worry about generalization. You just need to have a little bit of data for each possible value of the variable. When you have two variables, then you have, say, n-squared configurations of the variables. If you have three, you have n cubed, and so on. And of course, as the number of variables increases, for example, the number of pixels in an image might be easily 1,000 or 1,000,000. There's no way you're going to cover all the possible configurations of these variables. And so you need to really generalize in a powerful way. So this difficulty is called the curse of dimensionality. And it gets worse exponentially with the complexity of what you're trying to model. And what I believe is that in order to fight an exponentially difficult obstacle, you need to use other exponentials, something that is good for you in an exponential sense. And that's what compositionality gives us. Compositionality just means we're composing pieces together. This is how we program. This is how we speak. We have concepts that we combine together in very flexible ways. I mean, language is very much anchored in this. Engineering is very much anchored in this. So in deep learning, we already have some forms of compositionality. We have two forms of compositionality that I have studied in the last 20 years or so. So one is the idea of distributed representations, which actually comes from the early 80s in Jeff Hinton's work, which says that instead of having symbols, we have patterns of activation. So, a cat or a dog is not just an abstract, discrete symbol, but it's also a pattern of sub-symbolic attributes. And cat and dog can share some of these, and so you can generalize from the things you've learned about cats to things you can say about dogs. And then there's another form of compositionality which comes from having multiple levels in the neural net. So I'm going to explain a bit more. Regarding why it's interesting to have all of these patterns of activations, you can think of these as different features. So for example, at a particular level in a convolutional net, which looks at an image, you might imagine, and in fact we have identified, that some neurons will specialize for particular features, and sometimes those features can be actually associated with a name. So for example, if we're looking at images of children or of humans, we might have a neuron at that level that's detecting whether the person wears glasses, and then maybe another neuron is detecting whether the person is a female or a male, and then another one is detecting whether the person is a child or an adult, and so on. And you can see that now, if you have, say, 100 of these, you can have something like 2 to 100 combination of these attributes. So that's the exponential advantage, that once you learn about each of these features, you can generalize to new configuration of those features you've never seen. Whereas in more classical statistical non-parametric methods, like kernel machines, in a way you would need to see enough data to cover all of those configurations. So you would need exponentially more data to learn about these things. The other form of compositionality comes from stacking layers on top of layers on top of layers. And the hope that we had when we introduced deep learning at the beginning of this century is that we are able to get these compositions of functions to learn gradually more abstract features of the world. Ideally, we would like these high-level features to correspond to high-level abstractions of the kind we communicate with language, and that we can think of these abstractions as explanations, as factors of variations that are present in the data, just like in my previous example. And it would be the level at which you would like to reason, to do language understanding and generation, to be able to combine the things you already know to transfer to new distributions. So a lot of what I'm talking about today is trying to achieve this dream that we set to ourselves at the beginning of the century with deep learning, which I don't think we have achieved yet. So there's been a lot of interest in this idea in the last few years. People call it disentangling the factors of variation. But I think most of the work is not going in the right direction. It's assuming that those high-level factors are independent of each other. I think that's a too strong assumption. So if you take the kind of high-level factors which we manipulate with language, like cat and dog or fork and knife, they're not independent statistically. In fact, they get to be combined with very strong dependencies to form sentences. Another thing that is important to keep in mind is I don't think that there's going to be an easy solution to the problem of discovering those high-level factors in an unsupervised way. Of course, we can use supervised learning to tell us what they should be, but babies, for example, are able to figure these out in a fairly autonomous way, even before they learn language. So I think that the way we're going to do that is combine a number of priors or clues, sort of indications that the learning machine can exploit in order to identify those factors. For example, some of those factors speak about different temporal or spatial scales. And another thing I'll tell you about today is that the dependencies between those factors, even though they're not independent, but the dependencies are simple. And I'll tell you about the consciousness prior as one of the way to express that idea. And finally, many of those factors have to do with agency, with causality, with the fact that we human are not just passive observers of the world. We are embedded in the world, and we act in the world, and we learn from those interactions with our environment. And in doing so, we're constructing representations where some of those factors, many of those factors, actually are causal variables. In other words, they can play the role of cause and effect. And related to this is many of these are aspects of the world that we can have an effect on. So what I call controllable factors, which is not the case of low-level data like pixels. You cannot control pixels, but I can control the position of this object in my hand. So that's why I call it an object, and I don't call the pixels objects. So there is the question of learning and to discover those factors, but then and basically separate them from the mess which we have with low-level data like images. But then there's the question of what kind of operations I'm going to do with those variables, what kind of computations, what kind of dependencies exist between them. And one of the ideas that I'm going to try to tell you about today is that when you map the data to this high level of representation, something really nice happens, which is a lot of the knowledge, a lot of the dependencies between them, a lot of the information about the world that can be captured in that space can be modularized. In other words, can be factored out into small pieces that can be recombined in new ways. And I think this is one of the main advantages from a practical perspective of having these high levels of representations, is that it makes it easier to reuse those pieces of knowledge in order to generalize to new distributions, to new setups, to generalize in a more powerful way than standard approaches in machine learning. So let's go through some of these building blocks now that I'm going to try to explain to move towards this. So one of them that I mentioned briefly is this notion that many of the factors have to do with action in the world, have to do with how we can change things in the world. There's a theory in psychology, the theory of affordances, that says that the way that we represent objects in the world mostly has to do with what we can do with them. So a door is more about the fact that it allows us to move from one room to another room, and that we can open it or close it, and not so much about its shape. And you know, a cup is really about the fact that we can put liquid in it, hot liquid, and then drink, right? So that's the idea of affordances, and I think we can take these very abstract notions and turn them into mathematical formulas, which are like objective functions that put pressure on the representations to extract these kinds of factors that correspond to aspects of the world which we can control, as well as to policies, in other words, high-level actions that can modify those aspects of the world. So I introduced this idea in a paper in 2017, actually with my son Emmanuel, that's the E there. There's been a number of papers recently about how we can express this using a notion of mutual information between the representation of high-level actions or intentions and the representations of the state, of observations, of data. So when the mutual information between these representations is high, it means that there's like a simple mapping that relates our intentions or our policies with different dimensions of our representations of the world. Okay, so now let me tell you about attention mechanism, because I believe this is the most important ingredient that we have discovered in recent years of deep learning that will allow us to move to higher level cognition. So in 2014, we introduced a particular form of attention mechanism which is differentiable in order to do machine translation. The idea of attention is that the computation is going to be focused on one element at a time. And so we're going to go through a series of these computations where at each step we focus on one element. So at each step, what attention does is it selects The form of attention that we have introduced is called soft attention, particularly soft content-based attention. So the soft part means that we can train these things using our traditional backdrop methods, because instead of having a completely all or none decision about what you select, you have a sort of a probability over different elements that you can select, or a weight that you're going to give to different elements. So in machine translation, we use this to focus attention on one word or a few words at a time when you're translating and you're trying to find the next word to produce. Actually, a lot of that work was done with Kyung-Young Cho, who is sitting here somewhere and is, I guess, going to be speaking today as well. This has been extremely successful, and very quickly was adopted by Google Translate just a couple of years after our initial work, and has really changed the quality of machine translation. But more recently, these kinds of attention mechanisms have entered pretty much all of the state-of-the-art methods in natural language processing, using what's called self-attention, transformers, and so on. And I won't have time to go through this today, but we've been working since last year on the idea that we can use attention mechanisms also to bypass the very old problem of vanishing gradients, of long-term dependencies with recurrent nets. So that's one of the things I worked on in the 90s that remains an open problem, and I think that attention holds the key to really solving a lot of problems, avoiding the vanishing gradients. And the other thing about attention is it's also a key to consciousness, as I will explain. All right, so now let me say a few words about how we're going to think about the next step of deep learning. I mentioned high-level kind of cognition, but let me try to be a little bit more precise. Psychologists like Kahneman have proposed a distinction between two kinds of cognitive tasks, System 1 and System 2. System 1 is essentially everything you can do in an unconscious way. So a lot of perception is like this. Everything you do that seems intuitive, but that you cannot easily explain with words. Everything that you can do in a habitual way, like driving back home on a route that you know. That's the kind of thing that deep learning does quite well today. System 2 is about high-level cognition. It's everything you do in a conscious way. Usually it's going to be sequential, and it's going to go through a series of steps, so using attention. And it allows you to do things like planning. It allows you to do things like figuring out how to go from one place to another place in a city you don't know by first looking at the map and then figuring out what you want to do, and then you have to stay attentive while you're driving to pay attention to everything and sort of on the fly figure out what's the right thing that you have to do, rather than rely on a more habitual type of policy. System 2 is also what the classical AI based on symbols and logic was trying to achieve, reasoning. And so this is the kind of thing that I'm going to tell you about. I think we can extend deep learning towards. One of the subjects that I'll touch about, which is important, is that I don't think we can do just System 2. We have to do both of them together. And whereas System 2 really is highly linked to natural language, if we try to only take the ideas of System 2 alone without anchoring them in System 1, I think we're going to fail. So I'll tell you later about grounded language learning, where we're trying to build systems that understand their environment and can also communicate about it. So you have both language and a model of the world. Why I think that System 2 is important in a practical sense, I mean, besides being exciting because it's sort of the next frontier of cognition, is because it introduces a form of compositionality which comes in addition to the ones I told you about that deep learning already has. And that form of compositionality, that what allows you to figure out a new path when you go to a new city, it allows you to generalize out of distribution, to generalize in a systematic way, recombining the concepts you already know. Okay, so in this slide, you have a lot about the heart of the sort of plan that I'm trying to lay out for you for advances in deep learning towards System 2 cognition. So let's go back to attention and consciousness, actually. So what is a thought? If you do a little bit of introspection, you'll realize that a thought is a very low-dimensional object. In other words, a thought only refers to very few aspects of the world. And so there's got to be a mechanism that selects which aspects of the world which you could think about and brings them to your consciousness, and sort of selects them and puts them together into a thought. And then maybe half a second later, you have another thought, right? So, this is, we're talking about something different from what we've been doing with deep learning up to now. All right, let's talk more about consciousness, because this is a word that a lot of people hesitate to use, and I can understand that, because it remains a little bit fuzzy what it means. And, you know, for many decades, if not centuries or thousands of years, it's been a subject mostly of study by philosophers. So now I think we are at a cusp where computer science can start thinking about consciousness as a form of computation. You know, there's pretty much a scientific consensus that your brain is a machine. It's a very complex machine, probably stochastic, and part of it is the computation you're doing that makes you conscious. And it'd be really important to understand what that computation is, because it might help build more intelligent machines. Actually, when we use the word consciousness, we're often referring to different types of things that may be related to each other, but maybe we need to disentangle a little bit. So there's at least three things that people talk about when they talk about consciousness. There's what's sometimes called access consciousness. So that's a lot of what I'll be talking about today. The fact that, you know, a thought selects on a few aspects of the world that you're going to be somehow operating on. And you're going to be able to use this to plan, to imagine, to influence your actions. And we know from neuroscience that these conscious thoughts have a huge influence on the computation going on everywhere in the brain. It's kind of information that is broadcast to the whole brain. And it allows to unify a lot of the computation that is going on in the brain. Then there's the notion of self-consciousness, which for me is just a special aspect of you know, the things that you're thinking about. In the back of your mind, there's always a notion of where you stand, you as a person, as an agent, as part of your representation of the world. There is yourself, right? There's a sort of a reference to yourself. And sometimes that includes the social consciousness, like what's my role in a group, what's my role in society, and how that might even be related to things like moral values. Finally, there's another aspect of consciousness, which is subjective perception, also called qualia, which is probably the aspect which is most considered as unattainable by machines. I think it's a mistake to think that way. What it's about is the fact that the way that we perceive the world is subjective, is personal. And I think the reason it's so is because of two things. One is that it depends on the representations that we have. So each of us has a different history, different life experience, which means that our internal representations are different from each other. So like, for example, maybe for me, the color red means something positive emotionally, and maybe for you, it means something negative. And the other thing is, of course, that this access consciousness means that we are going to focus on different aspects of perception, right? All right. Why would we even care about consciousness? Well, it's something that evolved. Evolution has put that into us. And usually when evolution puts something in an animal, there's an advantage. And I think in the case of consciousness, there is a computational advantage. And I'm going to try to convince you of some of these advantages. So I think that's the reason why we want to study consciousness. We want to be able to understand the corresponding computations and why they are useful for intelligence. And the thing that I'm going to try to say is that they allow humans to perform more powerful, more flexible forms of generalization that the current machine learning that we have cannot do easily. All right. So 2 years ago, I started thinking about this, and I wrote a little white paper about my view of this. And it's called, the paper is called The Consciousness Prior. And it says that in terms of neural net architecture, in order to implement some sort of conscious processing, we're going to be using attention that I've been talking about. And we're going to have to think about two kinds of states at the high level of representation. A very high-dimensional unconscious state, which contains all of the information that you could be thinking about. And attention is going to select a few of them that go into short-term memory, that go into a thought, and those things that are selected go into a conscious state, which is this low-dimensional object I was talking about. So that's one aspect. But why do I call it prior? Because it implements a kind of constraint on the sort of computation that can be done, which can be interpreted from a probabilistic point of view as a form of sparsity in the joint distribution between the high-level variables. So what do I mean? Let me try to unpack this. Normally, in machine learning, what we do is we learn joint distributions, and they could be arbitrarily complicated. But there's something special about the way that high-level concepts are interrelated to each other. We can take a few of them and form something like a sentence, like, if I drop the ball, it will fall on the ground. And you can think of that as a rule. And it says something very powerful. In other words, that has a high probability. But it can do that using very few variables. Like, just the number of words here is small, right? And so this ability to capture highly probable events using very few variables at a time into pieces of knowledge that are separable from each other, like these sentences. That's a very powerful attribute, but it corresponds in a graphical model, so these forms of representations of the joint distribution, to sparsity of the structure of the graph that relates the variables together. So we call these factor graphs that would be appropriate here to talk about the joint distribution. And it would say that each of the factors, each of these rules, involve very few variables at a time. Okay. So there's another nice thing about consciousness and thoughts is that we can communicate them. In fact, the way that consciousness currently is studied in psychology and neuroscience is by asking people, what were you thinking about? What did you observe? What did you perceive using language? That's why it's hard to study consciousness in animals. We still study consciousness in animals by trying to find neural correlates of when a human is reporting about some conscious thoughts, what is going on in terms of neural activity, and then seeing the correlates, the similar activity in animal brains for similar tasks. So there's a very strong connection between consciousness and language, and I think this is something we need to exploit in machine learning as well. Because remember, one of the biggest, most important applications of machine learning is being able to have machines communicate with humans in natural language. So the fact that these high-level representations that I would like us to discover with our new machine learning methods have the property that they're connected to language through a very simple mapping, like it's like each of these high-level variables correspond to a word, is a very important property. And yeah, I think it's going to be key to progress in natural language understanding. The progress in these high-level cognition abilities and representations. So there's some interesting questions about how we should use natural language to guide the discovery of these high-level representations. If you think about it, right now, the way that we put high-level concepts in neural nets is we use supervised learning, where we tell the machine, this is a cat, this is a dog, this is a chair, and so on. And it's actually one of the reasons why supervised learning finds really good features, because we're using language to help push the neural net, the encoder, to develop good representations, because these representations are now going to be strongly linked to those high-level concepts. But we would like machines to also discover concepts by themselves, just like humans are able to. So there's a question of whether, if we're going to be learning jointly about how the world works and how to name things in the world, should we first have models that first figure out how the world works, like just not in a non-linguistic way, and then kind of put tags, put names on the things that it learns? Or should we learn these two things together? My inclination is that we want to learn these two things together. I mean, babies only start speaking after 1 or 2 years, but even before that, they are getting a lot of linguistic input. So last year, we worked on one of these projects that combine learning how the world works and learning how to communicate or to understand natural language sentences. So these sort of projects are called grounded language learning. And our paper was presented at the IACLR conference last spring. It's called Baby AI. And the idea was we would have this very simple environment with all kinds of objects. It was a partially observable environment, meaning that the agent only sees parts of it, which is the grayed out zone. And it would have a language that is compositional. So the way that language comes in is that the agent has to solve a mission, like in a video game, and the mission is specified in natural language. Things like put the blue key next to the green ball. So the other thing is we designed a series of gradually more complex tasks in this environment. For example, things very simple like go to the red ball, up to very complex things like put a ball next to a purple door after you put a blue box next to a gray box and pick up the purple box. I'm sure this is already too much for regular humans. But actually this is hard, and we found that with the current state-of-the-art methods in machine learning, in reinforcement learning, and imitation learning, it takes from hundreds of thousands to millions of examples of trajectories in order to learn these very simple tasks. So we know that humans can learn these things much faster. And so we think that there are some fundamental elements to our algorithms that are missing that need to be put in. So let me tell you about this. What is missing. I've mentioned it, but now let me focus on something very concrete where at the theoretical level we're missing something. All of learning theory in machine learning is based on the idea that the data on which we're going to test the system comes from the same distribution as the training data. This is called the IID hypothesis. And so there's no notion of generalization to something other than the kind of data we've seen during training. But humans and animals have to generalize in a somehow more powerful way. When animals move around the world, they enter new territories. They meet new peers. So the distribution that they're seeing changes. And they're still able to generalize somehow, right? So, for example, I can tell you a science fiction story. It's about some combination of concepts which doesn't make any sense in the real world, and so it has zero probability under your training distribution, but your brain is quite happy to imagine this counterfactual world. So it's very easy for us to reuse the things we know, to combine them in ways that have even zero probability under the training data. Or it might be just very rare. So the example of autonomous vehicle is interesting, right? So there's the very rare, dangerous, accident-prone situations. They're very different from your regular life, right? So I had one accident in my life. I was 18, and I had been driving for 2 years before that. So before that, I had zero examples of, how an accident would look like. And then for the rest of my life, I've been driving with a single example, okay, about this kind of situation. So somehow we are able to generalize to these situations that are very unlikely or even impossible. How do we do that? We do that because we're able to take the knowledge we have acquired and recombine it in new ways. Okay? That's the compositional idea that is in the title of my talk. Now, there is an idea that helps us maybe put a little bit of order in this notion of reusing pieces. And that idea comes from the book of Peters, Jensing, and Chalkov, which is an excellent book, which I suggest you to read, on causality. That has influenced me a lot. And in this book, they introduce this hypothesis, which I really like. The hypothesis that there's a lot about the world which we can understand by saying that what explains what we are observing is the composition of independent mechanisms. So let me explain what that means. Here, independent means not in a statistical sense, but in an information theoretical sense, that each of these mechanisms, which can be composed to explain the things we're seeing, don't tell you anything about any other mechanisms. And one way to see this is that if there was something that changed in the world in one of these mechanisms, you don't need to relearn the rest. You only need to adapt this particular mechanism which was modified. So this is something that we are starting to exploit, right, in papers this year, especially having to do with causality. But it has to do with how we can decompose our knowledge of the world in pieces. So you think about the graph on the left is a sort of a representation of the pieces of knowledge I have, and the edges represent interactions between those pieces. And then something changes in the world due to what we call an intervention, like somebody does something, somebody turns off the light, and suddenly it looks like everything is different, everything is dark. But there is a simple explanation. It's because this one bit changed, this one variable changed, corresponding to the switch that went from on to off. If we have the right representation of knowledge, in which the pieces are not things like pixels, but are things like switches and the kinds of concepts that we manipulate with language, then we can infer those changes, we can guess what's happened to explain those changes using very little data. So that's the importance of modularity. And it's not just any decomposition of knowledge, it's one that has a property that is robust to changes in distribution that happen in the real world because there are agents who do things, like turning off switches. So in recent work, this is going to be the last bit of my presentation, this is a paper that we have just put out called Recurrent Independent Mechanisms, RIMs. And it uses some of those ideas. It's one step towards some of the goals that I've been talking about. And it's a new form of recurrent neural network that uses attention mechanisms, that uses notion of objects to be manipulated by the network, and that uses a notion of modularity to decompose knowledge into separable pieces. So in this RIM model, you have different subnetworks corresponding to different modules, which we also known as the mechanisms. And there's going to be a selection of which mechanism are going to be active. So there's this attention mechanism or conscious access, which is going to select just a few of them. And the others are just going to follow some sort of default dynamics, because they evolve over time. They each have an internal state. And at each time step, the ones that are selected are the ones which find something interesting in the current input. So there's a top-down attention that's going to combine the current state of these mechanisms with what is currently being extracted, this unconscious state, in order to identify some elements of the input that are kind of interesting for some of these modules, and those pieces of information are going to be brought up to the selected modules. So at each time step, the modules are going to pick something from the input, and they are also going to communicate with each other in a sparse way. So instead of the usual fully connected structure that we have in neural nets, we have a sparse connectivity, but it's very different from just a sparse connectivity in the normal neural net, because it's sparse in a dynamic way. So at each time step, which module talks to which module is different. And it's, again, attention mechanisms which control which module talks to which module, based on the context. And the other big thing about these networks is that their inputs and their outputs are not the usual high-dimensional vectors that we have in neural nets. So, think about layers of a normal neural net. It's like one vector in, one vector out. Here, the inputs and the outputs of these modules are sets of vectors. And we can think of these elements in those sets as corresponding to objects. So those neural nets, they take objects as input and they produce modified objects as output. Okay, I'm not going to have a lot more time, but let's just give you a few examples of this working surprisingly well. So we've done, in particular, tests of out-of-distribution generalization, where we train these recurrent nets on various classical tasks, and we then test them on versions of these tasks corresponding to longer sequences or larger images. And they generalize much better than existing methods at these out-of-distribution benchmarks. We've also tested them as a replacement for LSTMs in, in reinforcement learning agents that play Atari, and we found that they work a lot better than the traditional LSTM. So everything above the bar, the 0, corresponds to a game where our RIMs do better than LSTMs on, as part of a standard LSTM PPO baseline for reinforcement learning in Atari. So each of the columns correspond to one of the Atari games. All right, so let me try to conclude. I think that we're building up a series of tools to help us construct higher-level cognition and introduce notions of consciousness in machine learning. One of those tools I didn't have time to go through is meta-learning, which is a way to adapt quickly to changes in distribution, but I talked about changes in distribution, and that's important. I've talked about the consciousness prior and the idea of sparsely interacting mechanisms at the top level, and the fact that we want to put pressure on the system 1 representations so that they extract high-level variables that have simple dependencies that can be represented in a modular way. And another aspect that I didn't have much time to talk about, but I talked a little bit at the beginning, is how this should be, system 1 and system 2 should be tied together so that agents can acquire an understanding of their environment, a world model, as well as a way to communicate about it, and then use this for reasoning and planning. This is some work that is ongoing in my group. Before I close, I want to mention that what we're doing here, I think, should be put in the perspective of what's happening in AI as our research goes out into the world and changes the world. And it can change the world in positive ways or in negative ways. And I think that researchers and engineers have a responsibility to think ahead of how their work is going to be used, for what purpose, and who is going to be helped by this and who might be hurt by it. So one of the things we can do, besides avoiding working on things that could be nefarious, is to work on applications that are going to help the planet, for example, improving healthcare, education, fighting climate change, and so on. And recently, I've co-founded an organization called AI Commons, which is going to try to help coordinate these AI for social good projects around the world. Thank you very much.